Hello, good evening. I'm Shivani Dhok and I welcome you for the week 8 session of this tutorial for the course of Principles of Signals and Systems. So, in this week, in the 8th week, the concept of Fourier transform was further extended for solving some examples, and its significance with respect to Bode plots and Hilbert transform was discussed. In the previous tutorial, I covered some questions, some basic questions related to Fourier transform, like how to find the Fourier transform and some properties of Fourier transform. But in this session, I'll focus majorly on how to use properties of Fourier transform further. Some 3-4 questions on Bode plot I'll cover, and one question on Hilbert transform, which will actually give you a glimpse of how this Hilbert transform is helpful in some situations. So before going ahead and solving the questions, let us first have a recap of the content that was covered in this week 8. So the first thing, while solving the questions related to Fourier analysis, which was Fourier series and Fourier questions, Fourier transform. So the first thing that was discussed was this periodic convolution. So what does this periodic convolution say? So it says that if I have two signals x1t and x2t, and these are periodic with common period t0. So both of these signals are periodic with period t0, then the circular convolution x tilde t, which is denoted something like this, normal convolution with this circle around it, and it is calculated with an integral over a period t0, let's say from 0 to t0, x1 tau, x2 of t minus tau d tau. This is the definition of periodic convolution, and it was seen that the Fourier coefficients for this are obtained as t0 times ck into dk, where the ck are the Fourier coefficients of this x1t and this dk's are the Fourier coefficients of this x2t. So this was the concept of periodic convolution. After this, the Fourier transform for two important signals. One was this signum function, that is sin t, and unit step function, and their interrelation was discussed. So initially the Fourier transform of this signum function was obtained as 2 upon j omega, and we had seen that this unit step function can be written in terms of this signum function as signum t plus 1 whole divided by 2, and the Fourier transform of this unit step function was seen as pi times delta omega plus 1 upon j times omega. So this was the Fourier transform of unit step signal. After that, the even and odd components of Fourier transform were discussed, and it was seen that this Fourier transform x of omega first can be separated in its real and imaginary parts, and its even part xc of omega is exactly equal to a of omega, and this odd component x odd of omega is equal to j times b of omega. So this is even component and this is odd component. After that, Bode plot was discussed. So it is a simple way or some simple way to visualize the frequency response of any system, and it is generally plotted in dB scale, and which is known as dB power. So this dB power is defined as, so if h of omega, this mod h of omega is magnitude response of any system with impulse response ht, then its dB power g of omega is given as 20 times, or let's say, yeah, is basically 10 times log to the base 10 of mod h of omega square, which is equal to 20 times log to the base 10 mod h of omega. After that, Hilbert transform was discussed, and the Fourier transform of this Hilbert transform is given as j times signum omega with a minus sign, and its time domain impulse response is given as 1 upon pi t. So this was the new concepts. These were the new concepts that were covered in this week. So now let us go ahead and look at some examples. So the first example that we are going to look today is this one, where the question is, find the Fourier transform. We need to find Fourier transform and not Fourier series of a train of impulse with period t naught, and its signal is given as delta t naught equal to summation k, where this k will be running from minus infinity to infinity, delta t minus k times t naught. So we need to find the Fourier transform of this signal. So let us first sketch this signal. So let's say this is my time axis. This is 0, t naught, 2 t naught, 3 t naught, and so on. This is minus t naught, and so on. So we have an impulse at t equal to 0, which is repeated at t equal to t naught, then at t equal to 2 t naught, 3 t naught, and so on, at every integer multiple of t naught, and also at negative parts, something like this. So this is time axis, and this is simply delta t naught of t. So basically this is a periodic signal. This train of impulse is periodic with period t naught, and we know that any periodic signal can be explicitly written or uniquely written with the help of linear combination of complex exponentials, which is nothing but Fourier series representation. So this delta t naught t can be written as summation k running from minus infinity to infinity ck delta t minus k times t naught, sorry, ck into e power j k omega naught t. Now the Fourier transform, you need to find the Fourier transform of this, is given as, using linearity property, will be simply summation of k running from minus infinity to infinity. This ck is independent of t, so we can just keep it outside, into Fourier transform of e power j k omega naught t, and this can be obtained as k running from minus infinity to infinity ck, and Fourier transform of this complex exponential is simply an unit impulse but at shifted version of it located at k times omega naught, and this omega naught is simply 2 pi by t naught. Now we know the form of this Fourier transform, and the only unknown that we have is this ck. So this ck can be obtained as 1 over t naught summation let's consider this interval from minus t naught to minus t naught by 2 to t naught by 2. So it is minus t naught by 2 to t naught by 2. In this duration, this this delta t naught t takes value as delta t, that is simple unit impulse, into e power j minus j k omega naught t dt. This is equal to 1 by t naught integral from minus t naught by 2 to t naught by 2. Using the shifting property, this becomes delta t, and e power minus j k omega naught into 0 is simply 1. So this vanishes off, and this is dt. And since we are integrating this impulse, from minus t naught by 2 to t naught by 2, the area under this region is simply equal to 1. So this ck is equal to 1 over t naught. Therefore, there is this Fourier transform of e power j k omega naught t is basically 2 pi into this unit impulse. Yeah. And therefore, this Fourier transform of delta t naught t simply equal to 2 pi by t naught by substituting the value of ck, k running from minus infinity to infinity, delta omega minus k times omega naught. Any doubts in this part? Okay. Let's go ahead with the next question then. So here what we are having is, we are having this question that suppose xt is sinc at square. So this is basically sinc of at whole square, and first we need to find the Fourier transform of this this xt, that is x of omega. After that, we need to find the Fourier transform of this signal xt, which is multiplied by this train of impulse, that is delta t naught t. So I am taking this example specifically because as you will be entering in the 10th week or in the 9th week as well, so there are some examples which are related to sampling. So that's why it will help in understanding those things in a better way. That's why I'm considering this example. So, and I'm considering this sinc at square to demonstrate some property of Fourier transform, which is multiplication in time. So let us first look at this signal. Let's say I have x1t is equal to sinc at, and we had seen in the lectures that, in the example taken in the lecture, that the Fourier transform of this is x1 of omega, which is equal to 1 by a pulse of 2 pi a dimension. So how does this look? So this looks something like this. This is omega axis. This is p. This is, let's say, x1 of omega, and this is minus pi a. This is pi a, and this looks something like this. And the height of this is 1 by a. So this looks something like this. A pulse of width 2 pi a from centered at 0 with height 1 by a. This we had seen in the example which is covered in lecture. Now the signal that we have been given is xt is equal to sinc of at square. So this I can write as x1 of t multiplied by x1 of t. Now if we look at the multiplication in time property, then Fourier transform of this is 1 over 2 pi x1 of omega convolved with x2 of omega. Normal convolution, linear convolution, not periodic convolution. It is simple linear convolution, and this comes out from the multiplication in time property. Okay, so the Fourier transform x of omega is given now as 1 over 2 pi x1 of omega convolved with itself, that is x1 of omega convolved with x1 of omega. I'm sorry, this is x1 of omega. Okay. So now let us try to find this convolution, this part. So what we are doing is we are considering x1 of omega convolved with x1 of omega. So for that, what we have is we have this x1 of omega as it is. If we flip it, so this is basically from minus pi a to pi a. If we flip it, it will remain same because it is symmetric with respect to this vertical axis. This is basically showing an even symmetry. So if I flip it, it will look exactly the same. So this is x1 of minus omega, again from minus pi a to pi a. And for convenience, let's say that this is minus, this is gamma and this is minus gamma. So basically what we are trying to find is this convolution, which you can write as minus infinity to infinity x1 of gamma into x2 of x1 of omega minus gamma d gamma. Now let's consider a case where this omega, let's say we have a case 1 when this omega is is less than minus 2 pi a. So this is the condition, something like this. This is minus 2 pi a, and this is something like this. So if I extend it here like this here, so this is minus 2 pi a. This is the reference, so this is basically omega equal to 0. So if my omega is less than minus 2 pi a, the situation is something like this. I'll have this omega somewhere here and there will be no overlap in such situation. So when I have this situation when my omega is less than minus 2 pi a, there is no overlap, and this convolution, let's say this is some y of omega. This y of omega is equal to 0. Now if I have case 2 where this omega is greater than, so this omega is greater than or equal to minus 2 pi a but is less than 0. So this is the situation, something like this. This omega is greater than 0 but it is less than this value here. Okay, this value means this omega lies between this minus 2 pi a and this 0. So the region of overlap is this. This is the region of overlap. So here y of omega is equal to, this point is minus pi a and this point here, I'm sorry, the region of overlap is this till this point, and this point is basically omega plus pi a. So this is omega plus pi a, and this amplitude is 1 by a, 1 by a, 1 by a. So basically 1 by a, x1 of omega is taking magnitude as 1 by a, so this will be 1 by a square d gamma. So this comes out to be omega plus 2 pi a by a square. Similarly, the third case, when my omega is greater than 0 and omega is less than or equal to 2 pi a. In that situation, let me just copy the same diagrams too. Yeah. Okay. So this will be a situation something like this, where this omega is somewhere here, this is omega plus pi a, this is omega minus pi a, and this 2 pi is somewhere here, 2 pi a, and again the region of overlap is somewhere here, something like this. So again the x of omega in the convolution, that is y of omega, is given as integral from omega minus pi a to pi a 1 by a square d gamma. So this comes out to be 2 pi a minus omega by a square. Again, when this omega is greater than or greater than 2 pi a, there is no overlap, and again this y of omega is equal to 0. So if we summarize it, this y of omega is equal to 0 if omega is less than 2 pi a or minus 2 pi a. It takes the value as omega minus 2 pi a by a square if omega is less than or equal to 0, is less than or equal to 2 pi a minus 2 pi a. Sorry. Minus 2 pi a less than or equal to omega less than 0. It takes the value as 2 pi a minus omega by a square if omega lies between 0 and 2 pi a, and again it takes the value as 0 when this omega is greater than 2 pi a. So if we sketch it, it's something like this. This is minus 2 pi a, this is 2 pi a. At omega equal to 0, it takes the value as, I'm sorry, this is omega plus 2 pi a. Yeah, it takes the value as, oh, also note there is a 1 by 2 pi factor here, so this x of omega is basically 1 upon 2 pi into y of omega. So at omega equal to 0, it takes the value as 1 by a. So we have a value, we have it something like this, and here the value is 1 by a. And this what we have sketched is simply x of omega. I hope this part is clear for this question. Let us look at the next part. So what we need to do is, we need to find the Fourier transform of this signal xt into delta t naught t. So let's say this signal is x tilde t, which is given as xt into delta t naught t, and the Fourier transform of this signal is again 1 over 2 pi x of omega convolved with Fourier transform of the signal delta t naught t. Now this we had seen in this question here. So this is the Fourier transform of the signal xt, this train of impulse, which is something like this, which is 2 pi by t naught summation k running from minus infinity to infinity delta omega minus k omega naught. So let us write down that. So let's say this is y tilde, x tilde omega. So therefore this x tilde omega comes out to be 1 over 2 pi x of omega convolved with 2 pi by t naught summation k running from minus infinity to infinity delta omega minus k times omega naught. This 2 pi gets cancelled. This is 1 over t naught summation k running from minus infinity to infinity. So we'll use the distributive property of convolution. So xt convolved with some summation of yt's is simply summation of xt convolved with each of that term. So we can write this as summation k running from minus infinity to infinity x of omega convolved with delta omega minus k times omega naught. And when we convolve anything with respect to impulse, we get the copy of the same signal at that point. So this is simply x of omega minus k times omega naught. And what was the value of this x of omega? This was what we had found. So basically, what does this mean? This equation means that we have replicas of x of omega scaled by a factor of 1 by t naught located at integer multiple of omega naught, which is simply 2 pi by t naught. So how does this look? So what we'll assume is this omega naught is very large compared to this 2 pi by a. So let's say this is 0, this is 2 pi by 2 pi a. So let's say this is omega naught, this is 2 omega naught, and so on. This is minus omega naught, minus 2 omega naught, and so on. This is omega axis, this is x tilde omega. Then let's say this is what we have. This is x of omega by t naught, and the maximum value here, it was 1 by a here, so it is 1 upon a by t naught. Then this is simply repeated at every integer multiple, something like this. At every integer multiple of this omega naught, we'll have one replica of x of omega, but it will be scaled by a factor of 1 by t naught. So this is the x tilde of omega. Any doubts at this part? Okay, let's look at the next question. So what we have been given is, we have been given a signal xt. So we have this signal xt is equal to 1 upon t square plus a square, and we need to find its Fourier transform. Now if you recall, that in class we had seen the signal e power a mod t, and let's say this a is greater than 0, a mod t, and its Fourier transform was obtained as 2a upon a square plus omega square. Now let us do multiplication of by 1 over 2 pi on both the sides. Because of linearity, it will affect both sides in a similar way. So 1 over 2a e power minus a mod t has Fourier transform as 1 over a square by omega square. Now look at these two signals, this one and this one. These two have similar forms. So whenever we have such things, we can exploit the duality property. So using duality property of Fourier transform, the signal 1 upon t square plus a square, and will have a Fourier transform of 2 pi x tilde of minus omega, where this x tilde of minus omega, x tilde of t, this x tilde of t is simply 1 upon 2 pi e power minus a mod t. So this is equal to my capital X of omega. Therefore what I have is x of omega is equal to 2 pi into 1 by 2a e power minus a times mod of minus omega, which is simply this 2 gets cancelled, pi by a e power minus a mod of omega. Any questions at this point? Okay. Let us look at the next question then. So the fourth question that we are going to see is we need to comment on the symmetry of real signals in two cases. The first one when they are even and the second one when they are odd. So for that we'll look at the discussion related to this even and odd components of Fourier transform, which we saw in the revision part of this lecture. So basically what was seen in the lectures was if I have a Fourier transform x of omega of some signal xt, of some real signal xt, so this I can write as a of omega plus j times v of omega, which I can also write as xe of omega plus x odd of omega, where this xe of omega is simply equal to a of omega and this x odd of omega is simply equal to j times b of omega. And what does this xe and x odd of omega signify? So this xt, this signal xt can be written in two parts. One is its even part, that is xe of t, so one part that we have is this xe of t plus x odd of t, and this capital Xe of t is Fourier transform of this signal, and we have this relation x odd of t has relation with its Fourier transform as capital X of t. Okay, now the first part that we have been given is xt is real signal. What does this mean? Xt is equal to x of minus t, which is equal to xe of t . So this I can write as xe of t plus x odd of t, which is equal to xe of minus t plus x odd of minus t. This right hand side I can simplify as xe of t, since even part is since xe of t is the even part, minus x odd of t. So if I compare these two terms, xe of t and xe of t gets cancelled. It simply means that 2x odd of t equal to 0, which means that x odd of t is equal to 0. Now what does it mean? This means that xt has only the even component xct, which is obvious because xt is a real and even signal. So if xe of t is if x odd of t is 0, if x odd of t is equal to 0, it simply means that capital X odd of t, x odd of omega is also 0, which simply means that x of omega is simply equal to xe of omega, which is even part of x of omega. This means that for a real even signal, x of omega is also even and real. Note that this xe of omega is simply a of omega, which is simply real part of x of omega, even and real. So this is an important property which sometimes helps us when we are working with the with some objective type questions. Okay, so now let us look at the second part of this question. So we need to repeat the same thing for odd signal. So the second part, what we have is this xt is odd signal. So what does this mean? X of minus t or x of t is equal to minus of x of minus t. So this we can again write as xet plus x odd t, which is equal to minus of x even t, x even of minus t, which is equal to x even t, minus x odd of t. So from where is this coming? So this is simply x odd of minus t is equal to minus of x odd of t. This is equal to minus xet plus x odd t. This gets cancelled. So we have 2 times xet is equal to 0, which means that xet is equal to 0. Therefore, x of t is equal to x odd of t, which means that x of omega is equal to x odd of omega, which is equal to j times p of omega. Okay. So again, this means that if my signal is odd, so for a real and odd signal, the Fourier transform is odd function of omega and is imaginary. This p of omega is simply imaginary part of x of omega. I hope this part is clear to everyone. If that is the case, then let us look at the next question, that is the fifth question. So in this part, we'll look at a very simple example where we have been given a system representation with the help of a differential equation. So this is the differential equation that we have been given. So let me write it again, what is given. So we have d dt of yt plus 5 times yt is equal to d dt of xt plus twice xt. This is the simple differential equation that we have been given, which is basically giving us the input-output relation. Another thing that we are having is this input we have been given as xt equal to e power minus 2t ut. Okay, now what do we need to find is we need to find the output of the system, which is y of t, for the given input. Now let us look at the time differentiation property of the Fourier transform. So by time differentiation property, this property says that if I have a signal with Fourier transform x of omega, so this xt has Fourier transform x of omega, then d dt of xt will have Fourier transform of j omega x of omega. So if I use this equation or use this property for solving this differential equation, then this d dt of yt will have Fourier transform of j omega y of omega plus 5 times y omega, which is equal to j omega x of omega plus 2 times x of omega. So I can take out this y of omega common, something like this. This is equal to j omega plus 2 x of omega. Therefore, y of omega comes out to be 2 plus j omega upon 5 plus j omega x of omega. Let me number this as equation number 1. Next what we have is this xt is equal to e power minus 2t ut. Now let us try to find what is x of omega. This is equal to integral 0 to infinity, because it's unit step function which is valid, which is non-zero only for 0 to infinity. So this is integral from 0 to infinity e power minus 2t e power minus j omega t dt. This can be simplified as 0 to infinity e power minus 2 plus j omega t dt. Since this 2 is greater than 0, it will tend to, this complex exponential will tend to 0 as t tends to infinity. So I can write this as minus 1 upon 2 plus j omega into e power minus 2 plus j omega t from 0 to infinity. So this comes out to be 1 upon 2 plus j omega. Now if I substitute this in equation 2 from equation 1, sorry, from 1, y of omega is equal to 2 plus j omega upon 5 plus j omega multiplied by x of omega, which is 1 upon 2 plus j omega, which is equal to 1 upon 5 plus j omega. Therefore this yt is equal to e power minus 5t. It is simply similar to this xt. It is similar to this xt. The only difference is instead of 2 I have a 5. So I can, this is equal to e power minus 5t ut. So this is the value of the output for the given system response and for the given input. I hope this part is clear. If not, please let me know. Otherwise, let's go ahead for the next question. So now let us look at some questions which are related to the Bode plot. Okay. So let us look at the very first transfer function that has been given to us. And it is h of omega is equal to 1 upon j omega plus 1000. Okay. So let us try to solve this. So what we have is this h of omega is equal to 1 upon j omega plus 1000. This I can write as mod h of omega square is equal to, or let's say I can write this as 1 upon 1000 upon 1 plus j omega upon 1000, which implies that this mod h of omega is equal to 1 by 1000 whole divided by under root of 1 plus, let's say it's square, 1 plus omega by 1000 square. Okay, so this is what we are having here. So now let us consider the cases. So by observing this, what is the corner frequency? The corner frequency is 1000 radian per second. So this is the corner frequency. So let us consider the case when, so the case 1, when this omega is much less than my corner frequency, that is 1000. In that case, this omega by 1000 is very small, much less than 1, which implies that this h of omega I can write as 1 by 1000 whole divided by 1, which is equal to 1 by 1000. Therefore, this g of omega comes out to be 20 times log of mod of h of omega, which comes out to be 20 times log to the base 10 power minus 3, which is equal to minus 60 dB. Okay, now let us consider the second case, that is case 2, where this omega is very larger than this corner frequency, and here omega by 1000 is very large compared to 1. Therefore, this h of omega can be written as approximately equal to 1 upon 1000 whole divided by j omega by 1000, which is equal to 1 upon j omega. Therefore, g of omega is equal to 20 log to the base 10 mod of 1 by j omega, which is equal to minus 20 log to the base 10 of omega. So this is what we have in this example. Now let us consider the case when, just look at the third case for which omega is equal to 1000. So in that situation, so let us first try to plot this. So let's say this is 1, this is 10, this is 100, this is 1000, and yeah, this is g of omega, this is log to the base 10 of omega, and okay, now let's say this line corresponds to minus 20, this corresponds to minus 40, and this corresponds to minus 60, till this corner frequency, that is omega equal to 1000. This g of omega takes the value of minus 60 dB, which is something like this, and after that we have a 20 dB per decade, minus 20 dB per decade slope. So after that it decreases something like this. So here we have minus 20 dB per decade slope. Okay, now this is the case for magnitude. Now let us look at what happens to angle. So this theta h is basically angle of h of omega. So in this situation here, when this omega is much less than 1000, my h of omega is approximately equal to 1 by 1000. So here theta h, which is equal to angle of h of omega, is simply equal to 0. Similarly, here when omega is very much greater than this j omega, very much greater than 1000, h of omega is approximately equal to 1 by j omega. So here theta h is equal to minus pi by 2. And suppose omega is equal to 1000, then in that situation this h of omega is equal to 1 by 1000 divided by 1 plus j omega. So the angle theta h is equal to 0. Angle of this 1 by 1000 is 0 minus 1 plus j. So this won't be j omega, this would be j because my omega is equal to 1000. So this 1 plus j has an angle of pi by 4. So this is equal to minus pi by 4. So if I draw this angle, so this is omega, this is theta h, this line corresponds to minus pi by 4, this line corresponds to minus pi by 2. Let's say this is 1, this is 10, this is 100, and this is 1000. At 1000 this takes the value as minus pi by 4. Before that it is all 0, and after that it is all pi by minus pi by 2. So it is actually something like this. So this thing on the left hand side is the magnitude response, and this on the right hand side is the phase response. So this is the Bode plot for this case. I hope this part is clear to everyone. Now let us look at the second part of the same question. So in this, now what do we have is same magnitude response, same Fourier transform, but now I have a square. So it is basically 1 upon j omega plus 1000 whole square. So let us try to find out, or let us try to draw the Bode plot for this question. Okay. Now what do we have is h of omega is equal to 1 upon j omega plus 1000 whole square. This I can write as 1 upon 10 power 6 upon 1 plus j omega by 1000 whole square. Okay, now again we'll draw the magnitude and phase response for this system, and again we'll have two cases. Again here we have corner frequency as 1000, and again we will be having two cases. So the first case is this omega is very much less than 1000. So similar to the previous case, this h of omega will be approximately equal to 1 by 10 power 6 upon 1, which is equal to 10 power minus 6. So from this g of omega, which is equal to 20 log to the base 10, 20 log to the base 10, 10 power minus 6, which comes out to be minus 120 dB. Similarly, theta h for this question is again this 10 power minus 6 is a positive constant, so this comes out to be 0. Now let us look at the case 2, when this omega is very much greater than 1000. In that situation, this h of omega is approximately equal to 1 upon 10 power 6 upon j omega by 1000 whole square. This thing gets cancelled, so it is basically minus 1 by omega square, and therefore this j of omega is equal to 20 log to the base 10 minus 1 by omega square with a mod. So this comes out to be minus 40 log to the base 10 omega. Now observe here, if I increase this omega by 10 radian per second, there will be a decrease of 40 dB. So this indicates minus 40 dB per decade decay or slope. Okay, and now this theta h comes out to be angle of this negative quantity which is equal to minus pi. Now let us consider the case when this omega is equal to 1000. Now here, if omega is equal to 1000, then this h of omega is equal to 1 upon 1000 10 power 6 common 1 plus j whole square. Now this 10 power minus 6 has an angle of 0, so this is equal to 0, and this 1 plus j has an angle of pi by 4, but it's in the denominator, so it will be minus pi by 4 multiplied by 2 times, because I am having a square here, into 2, so this is equal to minus pi by 2. So now let us draw the magnitude and phase response. So this is omega, this one is g of omega, this one is for theta h. Let's say this is 1, so let me 1, this one is for 10, 100 and 1000. This is 1, 10, 100, 1000. Similarly, this is 1, 10, 100, 1000. Now we know that let us first draw the magnitude response. So we know that this magnitude response is minus 120 dB till omega equal to 1000. So let's see, this is 120 dB or minus 120 dB. So this quantity, this is minus 120 dB, and it is like this, and after that I get a minus 40 dB per decade decay. So this is minus 40 dB per decade, and in reality this will go something like this. Okay, similarly here also, this won't be a sharp cut, but it will go something like this. Similarly, if we look at the phase is equal to pi by 2, minus pi by 2 at omega c, that is corner frequency, and it is minus pi after that. So let's say this is minus pi or minus pi, it's one and the same thing, and this is here, let's say this is minus pi by 2, and this is what we get at omega equal to 1000. Before that it is 0, then it goes to minus pi by 2, and then it goes to minus pi when my omega is very large compared to the corner frequency. So this is the Bode plot. This is the Bode plot. This is magnitude, and this is phase. Any questions at this point? Okay, let us look at the next question then. So again we'll look at the question corresponding to Bode plot, and here the transfer function that is given to us is this 10 plus j omega upon 100 plus j omega square. So before drawing, let us first write this in the standard form. So this h of omega is equal to 10, I'll take common, 1 plus j omega by 10 whole divided by 100 square, I'll take common, to 1 plus j omega by 100 square. So this I can write as, this is 10 power 4 and this is 10, so this is 10 power minus 3 into 1 plus j omega by 10 whole divided by 1 plus j omega by 100 square. So now if we observe here, we are having two corner frequencies. So corner frequencies that we have here is 10 and 100 radians per second. Okay, now let us try to consider two cases. So here instead of two, we'll be having three cases because we are having two corner frequencies. Okay, so let us look at the case 1. So the case 1 is when this omega is very much less than the first corner frequency, that is 10. So in that case, this h of omega can be approximately written as 10 power minus 3 into 1 upon 1 square, so which is equal to 10 power minus 3. So now this g of omega is equal to 20 log to the base 10, 10 power minus 3, which is equal to minus 60 dB. Let us look at the next case, and also here this angle theta h is simply equal to 0 because it is a positive number. The next case, that is case 3, is when this omega is much greater than 10 and is much smaller than the second corner frequency, that is 100. So here h of omega is approximately equal to 10 power minus 3 into j omega by 10 whole divided by 1. So this is equal to 10 power minus 4 is equal to 10 power minus 4 into j omega. Therefore g of omega comes out to be, so this g of omega comes out to be 20 log to the base 10, 10 power minus for omega, which I can write as minus 80 plus 20 log to the base 10 omega. So here what I am having is I am having a 20 dB per decade ka increment, and here theta h is equal to pi by 2 because it is an imaginary quantity with a plus sign. And the third case, this was case 2. The third case is when omega is much greater than 100. So here this h of omega is approximately equal to 10 power minus 3 into j omega by 10 upon minus omega square by 1000. So this and this gets cancelled, this and this gets cancelled, so it is equal to minus j by 10 omega. Therefore this j of omega is equal to minus 20 log to the base 10 of omega, and here this theta h is equal to minus pi by 2. Okay. Okay. Now let us try to draw this. So let's say this is magnitude, that is g of omega. This is theta h of omega. This is something like this. So we are having two corner frequencies, that is 10 and 100. So let's say this is 10, this is 10, and this is 100. Okay. Now it is like this. This is minus 60 dB. Till 10 it goes as minus 60 dB, something like this. After that we have a 20 dB per decade ka slope, which is something like this. So this is basically minus 40 dB, and after that again we have a slope of minus 20 dB per decade, which is something like this. Okay, this is omega, this is also omega. Now initially we have an angle 0. After that we have an angle of pi by 2. So this is pi by 2 and this is minus pi by 2. So in reality it will go something like this. Here also it will go something like this. Okay, let us look at the next question. Again, this is the last question for the Bode plot, and this is a little bit different question. So what we have here is a different case where the Fourier transform looks something like this. So what we are having is h of omega is equal to, I can write it in a simpler form, that is I can take this 10 common. So this is 1 plus j omega by 10 whole divided by this 10 power 4 I can take outside, 1 plus omega square by 10 power 4 into 1 plus j omega. So this is equal to, let me draw a line here. So this is equal to 10 power minus 3 into 1 plus j omega by 10 whole divided by 1 plus omega square by 10 power 4 into 1 plus j omega. Okay, now if you observe here, again we have 3 corner frequencies. First one is 1, second is 10, and third is this 100 power 2, that is, therefore it is basically 100 radian per second. Okay, now let us consider the cases for them. So the first one is case 1. So for this first case, this omega is much less than 1. So in this situation, this h of omega is approximately equal to 10 power minus 3, and therefore this g of omega is equal to 20 log base 10 power minus 3, which is equal to minus 60 dB. Similarly, theta h is equal to 0 because it is a positive quantity. Next case, that is case 2, is when omega less, this omega is much greater than 1, but is much less than 10. So in this situation, h of omega is approximately equal to 10 power minus 3 into j omega by 10, and remaining all will contribute as 1. So this is equal to 10 power minus 4 j omega. So here g of omega is equal to 20 log base 10 into 10 power minus 4 j omega with an absolute sign. So this comes out to be 80 plus 20 log base 10 omega. Okay, now let us consider the case 3. So here omega is much greater than 10, but is much less than 100. So this h of omega is equal to 10 power minus 3 into 1 plus j omega by 10 upon, this contributes as 1 j omega, so this also contributes as j omega by this. So this is equal to minus 40. So this is equal to minus 40 dB. Okay, so this is equal to basically 10 raised to minus 4. Let me be very precise. This g of omega is equal to minus 80 dB. Okay. Okay. The case 4, just a minute. So for this first case, when okay, so for case 4, we have this omega much greater than 100. So here 10 raised to minus 3. This is simply j omega by 10 upon omega square by 10 raised to 4 into j omega. Okay. Now this is basically 10 raised to minus 4. This goes above. This gets cancelled. This also gets cancelled. So this is equal to 1 upon omega square. So this comes out to be g of omega is equal to minus 40 log to the base 10 omega. So if we draw this, so let us draw just the magnitude plot for this one. So what we are having is, so till 1, oh, I'm extremely sorry, let us solve this entirely. There is a big mistake while solving it. Extremely sorry. Let us restart solving this from scratch to understand it in a better way. Sorry for this mistake. So what we have is the first case, that is the case 1 that we have is this omega is much less than 1, which means that everything goes to 1, which means that this h of omega is approximately equal to 10 raised to minus 3, which means that g of omega is equal to 20 log to the base 10 raised to minus 3, which is equal to minus 60 dB, and this theta h is equal to 0. The second case is this omega is greater than 1, but it is very much less than 10. So the factor that should prevail is this one and not this one. Initially I mistakenly considered this one. So this should prevail and rest all should take the value as 1. So this h of omega is approximately equal to 10 raised to minus 3 upon j omega. So this is basically equal to g of omega is equal to this minus 60 dB will remain as it is, minus 60 dB. So it is minus 60 minus 20 log base 10 of omega, and theta h will be equal to minus pi by 2. Now let us consider the third case. So the case 3 is when this omega is much greater than 10 but it is much less than 100. So here this h of omega is approximately equal to, now these two terms should prevail, this one and this one. So this is equal to 10 raised to minus 3. This takes the value as j omega by 10 upon j omega. So this is equal to 10 raised to minus 4, which means that g of omega is equal to minus 80 dB. And again this theta h, since this is a positive quantity, this is equal to 0. The case 4 is when this omega is much greater than 100. So here h of omega is approximately equal to 10 raised to minus 3 into j omega by 10 upon omega square by 10 raised to 4 into j omega. This j omega gets cancelled. This 10 raised to minus 4 gets cancelled. So what remains is j upon omega square. And now if I solve this, then this g of omega is basically equal to 20 log to the base 10 mod of 1 by omega square. So this comes out to be minus 40 log to the base 10 of omega, and this theta h, since we have, okay, since this j also gets cancelled with this, so it's only 1. So again this theta h is equal to 0. Now let us draw the magnitude and phase response. Okay, so this is g of omega, and yeah, this is h of omega. Now what we have is, to separate it out, yeah, this is theta h of omega, or simply theta h. This one, this is 1. The next corner frequency that we have is 10, and the next corner frequency that we have is 100. This is omega, this is omega. Okay, now from, if omega is less than, very much less than 1, so it takes the value as minus 60 dB. So till here it is minus 60 dB. After that we observe a minus 20 dB per decade decay. So it is something like this. So this is, if I draw it like this, this is minus 80 dB. After that it remains constant. Okay, so this is minus 80 dB, and after that again I have a decay, but now this decay is not of minus 20 but of minus 40 dB per decade. So it's a steeper slope, something like this. So this decay is of minus 20 dB per decade. This slope is of minus 40 dB per decade, and actually it will look something like this. Yeah. Now let us look at how the angle will look. So for everything till 1 it is 0, then it takes the value as minus pi by 2, something like this. Then it takes the value as 0 afterwards. So basically it will look something like this. Yeah, I hope this part is clear to everyone. So this was all about the Bode plot examples that I wanted to cover today. So let us now look at an interesting example which is related to Hilbert transform. So what we have been given is let xt be some band limited signal with maximum angular frequency omega m. So let us say that the signal looks something like this. The Fourier transform. So if my xt is a band limited signal, then its Fourier transform will be in a finite band duration, and let's say that it is a real signal, so let's say it is a symmetric signal. So if it is a real signal, its Fourier transform will be symmetric. Let's say it is something like this. Okay, let's say this is x of omega, this is omega m, this is minus omega m. Okay, so this is something like this what we have, and what we have been given is this x of omega is band limited, and suppose xct is equal to xt cos omega naught t, and xst is equal to xt convolved with ht sin omega naught t, where this omega naught is very much less than omega m. Sketch the Fourier transform of xst and xct, and this ht is basically Hilbert transform. Okay, so let us look at that Hilbert transform in the second part of the same question. To begin with, let us start with the simplest part where this xct, so this xct is equal to xt cos of omega naught t. We know the Fourier transform of this x of t is x of omega. So if we consider the time multiplication property of this Fourier transform, then the Fourier transform of this xt, let's say xc of omega, is given as 1 by 2 pi x of omega convolved with Fourier transform of cos of omega naught t. So let us again simplify this cos of omega naught t. So let us take this part only. So this is basically Fourier transform of e power j omega naught t plus e power minus j omega naught t by 2. And Fourier transform of any complex exponential is 2 pi delta shifted to that frequency. So this is equal to 2 pi by 2 inside the bracket delta omega minus omega naught plus delta omega plus omega naught. Therefore, this xc of omega is basically equal to 1 over 2 pi into x of omega multiplied by 2 pi by 2 inside the convolved with 2 pi by 2 delta omega minus omega naught plus delta omega plus omega naught. This I can write as 2 pi gets cancelled, so I have 1 over 2 x of omega convolved with delta omega minus omega naught plus x of omega convolved with delta omega plus omega naught. This comes out to be x of omega minus omega naught by 2 plus x of omega plus omega naught by 2. And let's say without loss of generality, this maximum value of x of omega is 1. So now if I sketch this, if I sketch this, it looks something like this. This is omega. This is, let's say, xc of omega. This is minus omega naught, and this is omega naught. So we have that this is 1 by 2 this frequency here is omega naught plus omega m. This is omega naught minus omega m. This is minus omega naught plus omega m. This is minus omega naught minus omega m. This factor here, this factor which is coming here, let me use some different color. This factor which is coming here is basically x of omega plus omega naught by 2, and this factor which is coming here is basically x of omega minus omega naught by 2. So this is the Fourier transform of xct, which comes out something like this. Now let us look at the second part of it. The second part is little bit more involved. So what we are having is this excess of t is equal to xt convolved with ht into sine of omega naught t. Okay. Now let's say this xt convolved with ht is some signal x tilde t. So let's say this part is x tilde t, which is, so this excess t can be written as x tilde t into sine of omega naught t. Okay, now let us look at this x tilde t. So let me number this as equation 1. So what we have is this x tilde t is equal to xt convolved with ht. Now note that we need to find the Fourier transform of excess of t. So let us first try to find out the Fourier transform of this x tilde t. So this x tilde of omega is equal to x of omega into h of omega. Now note that this h of omega is basically Hilbert transform, and we had seen in our initial discussion that this Hilbert transform has Fourier transform something like this. Okay, so this h of omega is basically minus j sine omega. So how does this look? So this basically looks something like this. So let's say this is h of omega. Okay, so for negative, so this is basically equal to j if omega is less than 0, and it is equal to minus j if omega is greater than 0. So this looks something like this. This is j and this is minus j. It looks something like this, and we know that our x of omega is something like this. Okay, so let me draw x of omega here. So this is x of omega. Okay, this is omega m. This is minus omega m. This is x of omega, and x tilde omega is simply multiplication of these two. So if I do this, so if I multiply these, what I'll get is, so if I multiply this, what I'll obtain is something like this. So let's say this axis corresponds to x tilde omega, and x tilde omega is basically multiplication of these two signals. So this part, this negative part will get multiplied by a factor j, and this positive part will be getting multiplied by a factor of minus j. So to indicate that, what I'll do is I'll just simply write j and minus j in the corresponding parts, which will correspond to the respective multiplications. So what I have here is I have this factor here and this factor here. This is omega m, this is minus omega m. This part, this negative part is scaled by a factor j, and the positive part is scaled by a factor of minus j. So this is x tilde of omega. So let me carry forward this part which I have onto the next page. So this is what we have obtained right now. Okay. But basically what we need to find is, we need to find the Fourier transform of this excess of omega, excess of t. So this excess of t is equal to x tilde of t multiplied by sine of omega naught t. So this Fourier transform excess of omega is basically 1 over 2 pi x tilde of omega convolved with Fourier transform of sine of omega naught t, which I can write as 1 over 2 pi x tilde of omega convolved with e power j omega naught t minus e power minus j omega naught t whole divided by this whole thing divided by 2j. And again these are complex exponentials, so these have a Fourier transform of 2 pi delta plus minus omega. So this is delta omega minus omega naught minus delta omega plus omega naught whole divided by 2j, and this is basically multiplied by 2 pi. So this 2 pi gets cancelled. This x tilde of omega convolved with deltas will just create a replicas at the respective positions. So this will be equal to x tilde omega minus omega naught minus x tilde omega plus omega naught whole divided by 2j. So this I can write as minus j, or let me keep it as it is. Okay. Now what does this signify? So the first two things basically simplify the simple shifts on the respective frequency components. So let me first just shift those components. So what we have is, let's say this is omega naught, this is minus omega naught, and this is omega naught, and this is basically the shifted version. And let me also consider this 1 by 2 factor. Okay, so this is the 1 by 2 factor here, and this one is the shifted version. Okay, so here we had j, this is minus j, this is j, this is minus j. Now if we consider this positive part, this factor, so this gets multiplied by 1 by 2j. So this 1 by 2 I have already taken care of. So basically this will be divided by j, divided by j. So this part, this positive part will be basically 1, and this negative part will be basically minus 1. Okay. It is similar to what we have obtained here, but now something else is happening. A different scaling is happening here. Similarly, if we consider this factor here, so this gets multiplied by minus 1 by 2j. 1 by 2 I have already taken care of, so this will be basically divided by minus j. This will be basically divided by minus j. So this part here will lead to minus 1, and this part here will lead to a 1. So what we have here is, we have a 1 here and we have a minus 1 here, and this is the Fourier transform of excess of omega. I hope this part is clear. Okay, if this is clear, then let us look at the last question that we need to do. So we suppose we just consider the same xct and xst from the previous examples. So now what we need to do is, we need to sketch the Fourier transform of x1 of t, which is given as xct plus xst. which means that this Fourier transform of x1 of t is x1 of omega is simply xc of omega plus xs of omega using linearity property. So now let us again sketch these two Fourier transforms. So what we have is something like this. Okay, so let's see, this is minus omega naught, this is omega naught, this goes like this. Here also we have omega naught and minus omega naught. This is omega axis, this is, let's say, xc of omega, this is xs of omega, this is, let me extend it above, this is 1 by 2, let's say this also indicates 1 by 2. So what we have here is something like this. Okay, so this is xc of omega. You can observe here it is simply xc of omega, which is simply scaled by 1. So let me explicitly write the scaling also. So these are just scaled by 1 1. Now if I consider xs of omega, it is something like this, but I have some different sort of scaling which we have seen in the previous thing. So we have something like this. Okay, so now here this part is scaled by minus 1 and this one is by 1. So we have something like this. And this thing, this x1 of omega, is basically addition of these two parts. Okay, now let us try to sketch that. So for that, let me shrink this a bit. Let me resize this. Yeah. Okay. So this x1 of omega is basically addition of these two. So I'm basically going to add these two, something like this. So this is 0. What I have here is my x1 of omega. This is omega 0. This is minus omega 0. Now let us just observe these parts here. If you consider this is just going to cancel out each other, and these two are going to add up to give a magnitude 1. Similarly, these two are going to cancel out each other, and these two are just going to add up and give me some constructive interference. So basically what I am going to get is something like this. Okay, this is omega naught minus omega naught plus omega m. This is omega naught minus omega m, and this magnitude is 1. This is omega. Now this, if you look at this factor, this x of omega here, okay, so this basically what happens is, this is a real signal and real signals show up conjugate symmetry property. Now if I modulate that signal to two carriers, something like this, so same things appear at two places, here as well as here. Now this part which is greater than omega naught, this part and this part are basically referred as upper sidebands, and this part which is less than omega naught and which is greater than minus omega naught, this part are referred as lower sidebands. So if I know that this x of omega is going to show some conjugate symmetry, so if I look at this part only, I will be able to understand or know what happens here. So there is no need to send this extra this extra information. This is just loss of bandwidth. We are not using the bandwidth efficiently. So instead of doing that, what we'll do is we'll just send this, and here by doing this we are just suppressing the upper sideband. So this is known as suppressed this is known as single subband transmission, so SSB. So I am just sending a single subband. Here I am sending the lower subband. Now let us look what happens in this case, the second case. So let me just copy this because I'm going to need it. So let me copy it here. So this is what I have, and this one x2 of omega I need to find, which is equal to xc of omega minus xs of omega. So now what we'll have is we'll basically have subtraction of these two signals, which will be looking something like this is omega. So this is basically x2 of omega. Let's say this is omega naught and this is minus omega naught. Okay. Now let us look at again those two bands. So now this it's subtraction. So this 1 minus 1, this will lead to a constructive thing. These will add up. But now this 1 minus 1, this will cancel out each other. So what I'll have is something like this. And since they're adding up, this will have a magnitude as 1. Similarly, here these two will cancel out because we are subtracting, and these two will get added up. So again, what I have is something like this. Okay, so this is what I have. Now here the lower subband is suppressed, but now I am sending the upper sideband. So this is also single sideband transmission. This is generally used in amplitude modulation case, and it helps in improving the bandwidth because I am using half of the bandwidth. So this is a practical application of this Hilbert transform, which is mainly used in communications. So this was all what I wanted to cover today. Hope this was an informative and useful session for you all. So if you have any questions, please let me know, else you are free to leave the meeting. Thank you.